Hi guys, so in this video we're just going to look at some different techniques for sorting. So suppose that you have some long list of numbers, so let's say 13, 10, 0, 4, 0, 5, 8. So you have some list of numbers like this, and we want to sort them so that the smallest numbers are at the front and the largest numbers are at the back. Now we're going to look at a couple of different methods. So the first one that we're looking at is called a bubble sort. And the bubble sort goes by looking at pairs of numbers, consecutive pairs of numbers. So we first look at 3 and 10, then we look at the next two, and the next two, and the next two, and the next two, and the next two. And we follow them through like that, and we simply ask ourselves each time if that pair of numbers are in the correct order. So for example, we start off when we say 3 and 10. Are they in the correct order? Yes, they are, because 10 is bigger. So we can leave them as they were. We then say, okay, compare 10 and 0. Are they in the correct order? No, they're not. So 0 and 10 should swap. Then we would compare, so we would have 10 over there. We would then say 10 and 4 and compare those. And in this case, we see they're in the wrong order, and so that those also swap. We then compare 10 and 0, and again, we see them in the wrong order, and so they swap. We see 10 and 5. We see they're in the wrong order, and so they swap. And then finally we see 10 and 8. And again, they're in the wrong order, and so they swap. 8 and 10. So we've looked at a pair of numbers, and then another pair, and another pair, and another pair. And if they were in the incorrect order, we swapped them. If they were in the correct order, then we left them as they were. And we can see that in one iteration of this, what we've essentially done is we've taken the maximum number, which in this case was 10, and we've moved it all the way to the end of the list. So after this first iteration, we can see that 10 is now in the final space. It's in the last space in the list, and we know that it's correct. So we never have to worry about moving 10 again. From there, we then perform another iteration. So we look at 3 and 0, and we see actually they're in the wrong order, and so they should swap. So it goes 0, 3. So we then compare 3 and 4. They're in the correct order, so they stay as they were. We compare 4 and 0. They're in the incorrect order, and so they must swap. So 0 and 4. We then see 4 and 5. Those are in the correct order, so they stay as they were. 5 and 8. They're in the correct order, so they stay as they were. Now, essentially what we've done is we've taken the maximum number from the sublist, excluding 10, and we've moved that to the end. Now, in this case, we were just lucky that that number happened to be at the end already. But so we can see that 8 is now there, and 8 is definitely in its final position, and we know that we never have to move it again. We then iterate through again, and we see 0 and 3. They're in the correct order, so they stay. 3 and 0, they're in the wrong order, and so we swap them. So we get 0 and 3. We then get 3 and 4. They're in the correct order, and we get 4 and 5. They're in the correct order. So we leave them. At this point, we can say that 5 has now been pulled to its final position, and we know that it's in the correct place in the sorted list. We then go back to the beginning, and we compare 0 and 0. They're in the correct place. We compare 0 and 3. They're correct. We compare 3 and 4. They're correct. So we've now gone through this entire list, and we haven't had to do a single swap. And so because we haven't had to do any swaps, it means actually that everything there is now sorted. So we've now sorted the list entirely. Okay, so now that the list is sorted, we can ask ourselves, how long did that take us? So in the worst case, we assume that we would have had to do some swaps over here as well, and then again and again and again. And so essentially what we would have had to do is we would have started off with a list of n numbers. Then after the second iteration, after the first iteration, 10 was in the correct place, and we then had to go through a list of n-1 numbers. And then after that, 8 was in the correct place, and we had to go through a list of n-2 numbers. n-3, 4, 5, all the way down until we had a list of one number. Now, that would be in the worst case where we would have to do a swap, at least one swap every time. We saw that when we didn't do any swaps, that section of the list was already sorted. So that would be our best case. So for now, we look at the worst case. And we see that if we're looking at a list like this, we're actually looking at, in this case, we do n-1 comparisons. In this case, we do n-2 comparisons. In this case, it's n minus 3, and it's all the way down until it's 1 minus 1. So it's 0 comparisons that are left. So if we want to count the total number of comparisons that we've done, we can simply add all of those up. And so if we say n minus 1 plus n minus 2 plus n minus 3 all the way down, that's exactly the same as saying 0 plus 1 plus 2 plus 3 plus 4 all the way up. So we can essentially say that the total number of comparisons that we make is going to be the sum of I going from 0 to n minus 1 of I. Now we know from maths that the sum of I equals 0 to n is simply going to be n plus 1 all over 2. So we're going to take that exact same formula, but rather than plugging in n, we're going to plug in n minus 1. So we can see that that is going to be equal to n minus 1 times n minus 1 plus 1, which will just be n all over 2. Once we've got that, we can multiply out, and we'll see that we get n squared over 2 minus n over 2. And so that's the total number of comparisons that we have to do, assuming the worst case where we have to go all the way through and we never get to stop early. So if we've got that, we can say that our bubble sort in the worst case then is going to give us order n squared, because we see n squared number of comparisons, and that's going to dominate as n gets really big. That's going to be much bigger than this, and so we get our n squared. Now we said that that was in the worst case. So the worst case we said was when we never get to stop early, when we always have to do some swaps in every single one of the iterations. Now we can see actually that that will happen in the case when the list is sorted backwards. So 5, 4, 3, 0, 0. If we see that our list looks like that, then in our first iteration, what will happen is the 10 and 8 swap, then 10 and 5, then 10 and 4, 10 and 3, 10 and 0, 10 and 0. And so we would end up having pulled our 10 all the way to the back of the list, and that would now be in its final place. We would then say 8 and 5, and they would swap. 5 and 4, and they would swap. 4 and 3, they would swap. 3 and 0, they would swap. 8 and 5, 8 and, let me write this out. 8 and 5 swap. 8 and 4 swap. 8 and 3 swap. 8 and 0 swap. And 8 and 0 swap again. Like that. And so again we see that it's pulled 8. In the next iteration, 5 would swap with all of these numbers, and 5 would end up over there. Then 4 would get pulled all the way, then 3 would get pulled all the way, 4 would get pulled, 3 would get pulled, and our zeros would get pulled. And so in that case, that's our worst case, and that's when we end up doing the n squared number of operations. In the best case, we see that our list is already sorted. So if we had 0, 0, 3, 4, 5, 8, and 10, we would say, should 0 and 0 swap? No. Should 0 and 3 swap? No. Should 3 and 4 swap? No. Should 4 and 5 swap? No. Should 5 and 8 swap? No. 8 and 10? No. And so because we haven't done any swaps, we see that the list is already sorted, and in that case we can stop. And so in that case, we ended up doing n minus 1 comparisons, which means that in the worst case it's n squared, and in the best case it's going to be order n. So that was the bubble sort. Our next sort we're going to look at is called an insertion sort. Now, in an insertion sort, we maintain two lists. So we can take our original list, and we pretend that it's actually two lists next to each other. So it's stored next to each other in memory. And what we do is we say we have some sorted list and some unsorted list. And so our sorted list, we say everything on the left-hand side of the blue line we assume is sorted, and everything on the right-hand side is unsorted. So now, when we've got a list of just one number, we can say that it's already sorted. We then take the very next number over here and we want to insert it into our sorted list. So in this case, we say, okay, we want 10 to be part of our sorted list. Should it swap with 3? Are they in the correct order? Yes, they're fine. So we leave them as they are. We then say, okay, we take the next number from our unsorted list and we want to insert it into our sorted list. So in this case, we can say that 0 and 10, we ask, do they swap? And we see that they do. So we say, should they swap? Yes, they do. So 10 and 0. We then say 0 and 3, and we say, should they swap? And again, yes, they do. So we swap those two, 0 and 3. We've now taken the 0 from the unsorted list, and we've inserted it into the correct place in the sorted list. We then do that again. So we say, take number 4, the first number in our unsorted list, and we insert it into the correct place in our sorted list. So we say, should 4 and 10 swap? Yes, they should. Should 4 and 3 swap? No, they shouldn't. And so in this case, we know that 4 is now in its correct place in the sorted list. We then take the next number and we say, okay, it's a 0. So should it swap with 10? Yes, it should, because it's less than 10. Should 0 swap with 4? Yes, it should. Should 0 swap with 3? Yes, it should. Should 0 swap with 0? No, it shouldn't, so we know that it's in its final correct place. And so we can see now that our sorted list has grown by 1 and our unsorted list continues to shrink. So we can then say, okay, take the next number from our unsorted list and insert it into the correct place in our sorted list. So we do that by saying, should 5 and 10 swap? And in this case, yes, they should, because 5 is less than 10. So 5 and 10 swap like that. And we then say, should 5 and 4 swap? No, it shouldn't, because 5 is bigger. And so in that case, it's correct. We then take our last number and we say 8, and it needs to be inserted into the correct place. So should it swap with 10? Yes, it should. We then say, should it swap with 5? And we see that it shouldn't, because 8 is bigger than 5, and so therefore it's in the correct place. And now that our unsorted list is empty, we can see that our sorted list has everything in it, and it's all correct. So to recap, an insertion sort has a sorted list, followed by an unsorted list. All right. And at every iteration, we take one number from the unsorted list and we insert it into the correct place in the sorted list. And so what this really means is that we have to take whatever numbers are on the sorted list and we have to move them up by 1 until we create the open space in the correct place to insert our new number. So we take a number and we insert it into the correct place. So let's have a look at the complexity. So in the first case, at the very beginning, we have one number in our sorted list. We take a new number from there, and we need to keep shifting numbers over and comparing with them until we get this number into the correct place. So potentially on the first one, we need to do one comparison. In the second round, we take a number from our unsorted list, and we potentially, in the worst case, have to compare it to every single number in the sorted list. So at this point, there are 2 items in the sorted list. In our next iteration, in the worst case, we would take this number, and if it had to go all the way back to the beginning, so if it was smaller than everything that was there, we would have to compare it to every single number in the sorted list. And so we can see the pattern developing here, that as our sorted list grows, in the worst case, we have to compare the new number to each item in the sorted list. And so that keeps going until we eventually get to the case where there's just one number being inserted. Now in this case, it potentially has to be compared to every number in the sorted list in the worst case. And so in that case, there would be n-1 numbers in the sorted list. So if we say how many comparisons are we doing? Well, this number gets compared to n minus 1. Okay, so all of these together make up the total number of comparisons, and so we're in basically the same situation we were with the bubble sort, and so we're saying that the total number of comparisons is going to be I equals 1 to n minus 1, and we said that the answer to that would be n minus 1 times n over 2, which again is going to give us something that is order n squared. So in the worst case, the insertion sort says that we do an n squared amount of work. Now what is that worst case? Well, we essentially said that it was when we took off a new number and we had to compare it to every single number in the sorted list. So in this case, what it means is that the new number that we're inserting is less than everything else already in the sorted list. So what that means is that our list would be in decreasing order. So in this case, we would have it like this. We would say 8 would need to compare all the way until it was at the very front of the sorted list. So 8 would be compared with 10 and they would swap. We then get 5. 5 needs to be compared with 10 and it's smaller, so they swap. 5 gets compared with 8, it's smaller, and so they swap as well. Same thing with 4, same thing with 3, and we see that in every case it has to go all the way back to the very beginning of the sorted list. And so we end up doing more and more and more comparisons as that list grows, and so we see that we end up with our n squared. In the best case, we're saying that we only have to compare it with the one item and we say it's already in the correct place. And so in that case, that happens when the list is already sorted. So when it looks like this, we would say 0 and 0, they get compared, and there's no swap. We then say 3 and 0, they get compared, there's no swap, they're already in the correct place. 4 gets compared with 3, it's already in the correct place. 5 gets compared with 4, already in the correct place. 8 gets compared with 5, already in the correct place. 10 gets compared with 8, and it's already in the correct place. So in that case, we see that we only ended up doing one comparison for each of these, and so we see that it's going to be linear in some way. So we don't have to compare the first number with anything, but then we compare the second, the third, the fourth, the fifth, the sixth, the seventh, all the way through until n, and so we end up doing a total of n minus 1 comparisons, which in our big O notation is going to be n, big O of n. Alright, so we now understand the insertion sort. Our next one is a selection sort. Now, in the insertion sort, we divided the list into a sorted and unsorted section. We're going to do the exact same thing in this one, except here we start off with an empty sorted list. Now, the idea of the selection sort is that we search through the entire unsorted section and we look for the smallest number. Once we found the smallest number, we then insert it at the end of the sorted list. So, in the previous one, we simply took the first number and inserted it into the correct place. Now we're going to say we're inserting at the end of the sorted list, but we need to select the correct number to use. So we start off and we see 3. And so that's the first number we've seen, we say that that's the minimum. We then find 10 and we say, okay, no, 10 is bigger, so it's fine. We find 0, compare it with 3, okay, 0 is actually smaller, so that means that 0 is our new minimum. We then go on and we see a 4. 4 is bigger than 0, and so 0 is still the smallest. We find a 0, it's equal to, so we don't worry. We see a 5, it's bigger than 0, so we don't worry. We see an 8, it's bigger, we don't worry. So we've now searched all the way through this entire list, and we found our smallest number. We can then say, okay, this is the first iteration, and so the end of our sorted list is going to be where the 3 is. So in that case, we simply do a swap, and we say that 0 goes there, 3 goes there, and the end of our sorted list is now over there. So we've now got the first number into our sorted list. Once again, we then search through, we start off and we say, okay, 10 is our smallest number, compare it with 3, okay, no, 3 is smaller, so that's now the smallest number we've seen. We see a 4, Okay, it's bigger, so we carry on. We see a 0. Okay, that's now the smallest number we found. So we're now using 0. We then see a 5, which is bigger, and an 8, which is bigger. So in this case, we can see that 0 is the smallest number in the unsorted list, and we swap that with the item in the next space that we need to insert. So we swap 0 to there, and 10 goes over there. So that means that the end of our sorted list is now before 3. We then go through and we say, okay, where is our next smallest number? Well, we see 3. Okay, that's our smallest number. We then compare it with 4. Nope, still smaller. We compare it with 10, still smaller. We compare it with 5, still smaller. 8, still smaller. So we see that our smallest number is actually in the right place, and so we don't actually have to swap it, but that's fine. So that's our next iteration. We then see a 4. 4 is our smallest number. Compare 4 and 10, 4 and 5, 4 and 8. Okay, 4 is our smallest number, and so we say that it's already in the correct place. We then see 10. 10 is our smallest number so far. We compare it with 5. Okay, 5 is smaller, so that's now our smallest number. We then compare it with 8. Okay, 8 is bigger than 5, and so we've gone through the entire unsorted list, and we see that 5 is the smallest number. We then swap it with whatever's in the open space. So 5 goes there, 10 goes there. And the end of our sorted list is now after 5. We then look at this one and we say, okay, 10 is the first number we see, so that's the smallest number. We then get an 8. Okay, 8 is smaller than 10. So 8 is our smallest number. We get to the end of the list. And so from here we can say 8 needs to swap with the next space that we need. So 8 and 10 swap, like that. And there's now one number left in our list, which means that it must be the smallest number, and we would swap it in with its own space. And so we can just say that it stays where it is, and there we go. We've now sorted the list. So the idea of the selection sort is that we have our sorted list, we have our unsorted list, we search through to find the minimum value in the unsorted list, and then we swap it with whatever's the next open space. So whatever number's here moves to the space of our minimum number, and our minimum number moves over there, and then that number is now part of the sorted list. Okay. Now, because the right-hand side is unsorted, we have no way of knowing whether we've got the minimum value unless we've actually compared our current number with every other number in that list. So the first time, in order to find the minimum value, we have to actually look at every single number in that list. And so we have to look at n different numbers, which means actually that we do n-1 comparisons. Then in the second round, we've taken one number out, so the unsorted list is now n-1 in length, which means that we have to do n-2 comparisons. We then have, we then have n-2 numbers, and then we end up doing n-3 comparisons. And we keep going all the way down until we've got 2 numbers. In that case, we do 1 comparison, and then in the case when we've only got 1 number, we don't have to do any comparisons. So from there, our total number of comparisons, we can add them all up. So once again, we get the sum of I equals 0 up until n-1, and so we know that that's n-1 times n all over 2. So again, we see that this is order n squared. Now, a catch here was that in order to know that we had the minimum number, we always had to search through the entire unsorted list. So in this case, there's no best case or worst case, because no matter what, even whether the list is completely sorted or unsorted or backwards, it doesn't matter. We always need to look through the entire unsorted list in order to know that we've picked up the smallest value. And so there is no best and worst case for this one, unfortunately. Okay, so we've then looked at 3 different types of sort. We've got our bubble sort, we've got our insertion sort, and we've got our selection sort. So we said that in the worst case, in the best case, how much work do we do in each? So for the bubble sort, we said that the worst case was when we always had to do at least one swap in an iteration. And that happened when the list was reverse sorted. And in that case, it was n squared. We said that the best case was when it was already sorted. And in that case, it was linear, because in our first iteration, we didn't have to do any swaps, and so we knew that we could stop immediately. In the insertion sort, the worst case was when our new number that we've picked up to insert had to be swapped all the way back to the very front of the list. And so again, that was when the list was in reverse order, and that gave us n squared complexity. The best case was when the list was already sorted, and it meant that we didn't have to swap the new number with anything, because we only had to compare it with the last number in the sorted list, and so in that case we got a linear amount of work. For the selection sort, we said that regardless of what happens, we always have to search through the entire unsorted list in order to know that we found the minimum value. And so there is no best and worst case, they're always the same, and it's always going to take us n squared amount of work. Okay, so that's the first three sorts: bubble, insertion, and selection sorts. They're fairly straightforward to remember. Just remember that the bubble, you have all those little pairs, and as you have those pairs of numbers, those are your little bubbles that you look at. Your insertion sort says take the first number from the unsorted list and insert it into the correct place in the sorted list. Your selection sort says don't take the first number anymore. It says search through the entire unsorted list and select the correct number to insert at the back of the sorted list. So the next sort that we're going to look at is called a merge sort. And the merge sort basically says that in our previous sorts, the amount of work we did was quadratic, right? So as the list got bigger, it became much more difficult to sort, right? So the idea of the merge sort is to say, well, we can sort a very short list very quickly. We know how to sort a short list. So if we can sort two short lists and then somehow merge them together in some clever way, then maybe we can come up with a better kind of sort. So the idea behind that is to say, if we have a list of numbers, right? So I'm going to add in one more number just so that the tree works out nicely, but we will we'll try different length lists soon. So suppose we have this list of numbers. If we can somehow break it into two, and if we can get the one side sorted and the other side sorted, in fact I see this is not a good example for this. Let's maybe say 9 and 0 can go like that. Okay, so say we have these two lists. So we have the left-hand side and the right-hand side. If we somehow know that A is 0, 3, 4, 10, we know that it's somehow sorted, and B is then 0, 5, 8, 9, and that one is somehow sorted. Can we then take these lists and combine them into one bigger one in an efficient way? And the answer is yes. So all we have to do is look at the front of each list. So we look at the front and we see, okay, they're both zeros, so in this case it doesn't matter, so we just pick one of them. So we can take 0 out. We then look at the front of each list, so 0 and 3. Which one is smaller? 0. So we take 0 out, we look at the front of each list, and we see 3. So we take that out, we look at the front of each list, and we get 4. We look at the front of each list, and we see 5. We look at the front of each list, and we get 8. We look at the front of each list, and we get 9. And the bottom list is now empty, so we can just take whatever's left at the top, and we get 10. So we can see that it was quite easy then to take the two sorted lists and merge them together into one big sorted list. Now, in the best case, we say that all the numbers in one list are smaller than the other. So suppose that we had 0, 1, 2, 3, and we had 4, 5, 6, 7. Now, we would look at the front of each list, we take a 0. We look at the front of each list, we take a 1. We look at the front of each list, we take a 2. We look at the front of each list, we take a 3. And this list is now empty. And so, because the one list is empty, we know that we can simply take whatever's left there and insert it into our final sorted list. So, how many comparisons did we do? Well, we ended up doing n over 2, because there were n numbers in total. We did comparisons until the one list ran out, and once that list ran out, we could simply copy whatever was left into its final space. So, in the best case, we do n over 2 number of comparisons. In the worst case, we end up alternating between them. So in the worst case, we might have something that looks like that. We look at the beginning, so we look at the front of each list and we get a 0. We look at the front of each list and we get a 1. We look at the front of each list, we get a 2. We look at the front, we get a 3. We look at the front, we get a 4. We look at the front, we get a 5. We look at the front, we get a 6. We look at the front, we get a 7. And so, in that case, we can see that we ended up doing n minus 1 comparisons in total. So, in the best case, it's n over 2. In the worst case, it's n minus 1. All right. But in either case, we see that we can do this merge in a linear amount of time. So if we can take the list, divide it into 2, sort the left and the right, and then merge them together in some linear amount of time, we can ask ourselves how long is that going to take us in total. So let's go back to our original list. We said that we have A and B. How can we sort the left and the right hand side? Well, we can simply do it recursively. So assuming that we know how to sort, assuming we can do a merge sort on the left and a merge sort on the right, we can get two sorted lists and then we can merge them back together. So that was our list. So we say divide it into 2, sort the left. How do we sort the left? Well, we do a merge sort. So we divide it into 2 and we sort the left. How do we sort a list of 2 numbers? Well, we divide it into 2 and we sort the left. So we see that we now have a list of 1 item. Okay, we can consider a list of 1 item to be sorted because it's already in whatever order we want it to be because there's only 1 item. So it means that that list is sorted. We then do the right. So once again, we've only got 1 number, so we say that it's sorted. So from there, we can now merge the 2 together. And so we look at the front of each list, and we say, which one is smaller? So in this case, we take 3. We look at the front, okay, this list is now empty, so we can just take whatever's left of the right-hand list, which gives us 3 and 10. We've now sorted the left, let's sort the right. So we have a list of 2 numbers. How do we sort it? Well, we divide it into 2, and then we sort the left. So we now have a list of 1 number, which is 0. Okay, we consider that to be sorted. We then look at the right. We have 1 number, which is 4. We consider that to be sorted. So we now have 2 sorted lists. We can merge the 2 together. So we look at the front of each. We take a 0. This list is now empty, so we take whatever's left on the right-hand side, and we get 0 and 4. We sorted the left, we sorted the right. So now we say, how do we merge these together? Well, we simply look at the front of each list and we say, which is smaller? So in this case, it's 0. So we can take 0 We then look at the front of each list. So we've got 3 and 4, which is smaller, so we take 3. We look at the front of each list and we say 4. And because this list is now finished, we can take whatever's left on this side and just insert it at the end. So that gives us those 4 numbers sorted. We then look at the right-hand side and we say, okay, we have a list of 4 numbers. How do we sort it? So we divide it into 2. We look at the left-hand side. We divide that into 2 and we see that we get a number by itself and a number by itself. We then take those and merge them together. So we look at the front of each side and we take the smallest value. This list is now empty, so we take the other side. So we take 9. The left is now sorted, so we look at the right. So we divide it into 2. We now have a list of 1 which is sorted and a list of 1 which is sorted. We merge them together by saying take the smallest number from the front. Then that list is now empty, so we then take whatever's left. So 8. We now have the left sorted and the right sorted, so we merge the 2 together. So we take the smallest first number, so we get a 0 and a 5, so we take the 0. We then get a 5 and an 8, we take the 5. We get an 8 and a 9, so we take the 8. This list is now empty, so we take whatever's left and we insert it into the list. Finally, we've got the left sorted, we've got the right sorted, so we can merge the 2 together, and we say take the first number. Okay, so we compare the 2 lists, we get a 0. Doesn't matter which one we take it from. We then compare the front again, and we get another 0. We then compare the front of the lists, and we get a 3. We compare the front, and we get a 4. We compare the front, and we get a 5. Compare the front of each list, so 10 and 8, and we get an 8. 10 and 9, we get a 9. The right-hand list is now empty, and so we can simply take whatever's left in the left-hand list and insert it down, and we see that we get our sorted list. All right. So the question then is, how much work did we do? Well, we can look at this and we can see that this is actually forming some kind of binary tree. And so in this case, it looks like it's a perfect binary tree. So we can look at it and say, if we turn this upside down, we get our big list, and that was made up of 2 smaller ones, and that itself was made up of 2 smaller ones. And each of those were made up of 2 smaller ones. Just like that. And so we can see that we took lists of length 1 and merged them together into a list of length 2. Then we did the same on the right. We then took 2 lists of length 2 and merged them together to form a list of length 4. We did the same thing on the right hand side. So we took all the lists of length 1, we merged them together to get lists of length 2. Those were merged together to get lists of length 4. Those were merged together to get lists of length 8. So what we can do is we can say, well, we know that in the best and worst case, a merge always takes us a linear amount of time. Okay, so we know that a merge here will take a linear amount of time, here it will take a linear amount of time, here and here. So all of those merges together take some linear amount of time. Order n. But we know that n was quite small at that point, but we did a whole bunch of merges. So although the lists were much smaller, we did some multiple of those things. We did multiple merges. We then do the same up here, where we say, okay, the lists are slightly bigger, but it's still linear to merge. So we merge there and we merge there. So the length of the list was still smaller, but we did it for we did 2 merges. Then over here, the length of the list is now bigger, but we still do a linear amount of work to merge them. So again, we've taken them and we've now done 1 merge in order to get there. So we can see that on each level of the tree, we've done some linear amount of work. If we do a linear amount of work at each level, and we know that there are h levels, some height of the tree. That's how many times we have to merge. So what is the height of a perfect binary tree like this? Well, we know that that's going to be logarithmic in some way, so log n. So if we do a linear amount of work, log n times, we see that overall the amount of work we do is going to be n log n. And so we can say that the merge sort in total is going to take us n log n comparisons. Now, in your algorithms course next year, you'll do a much more formal proof of this. But for now, that's just a bit of an idea of why this takes n log n. Now, this worked out really nicely because our list had exactly 8 numbers in it. Okay, so we had 2 to the power of 3. And in that case, we can see that there was 1, 2, 3 levels of merging, right? So what happens if the list is not a nice power of 2? So let's say that our list was rather 3, 10, 0, 4, 0, 5, 8. So in this case, there are now 7 numbers. So we can look at it in exactly the same way as we did before, and we can say, well, let's do the merges. So we can say 3 and 10, those get merged together, and we end up with 3 and 10 as before. 0 and 4 will get merged together, and we end up with a list of 0, 4. This is not a great example. Maybe let's swap these numbers around. Let's say 4 and 0. Okay, so those two get merged together, and we would get 0, 4. We would then say 0 and 5. Those would get merged together, and we get a list of 0 and 5, all sorted. Now, the one catch is that we've got this extra 8 now sitting here that there's nothing to merge with. Usually, it would have some other number there if we had 8 numbers, and those would merge together and it would all work out nicely. In this case, we simply don't need to worry about it, and we leave it for now. So we can then see, okay, well, these two would get merged together, and so we would get 0, 3, 4, 10. Right? We would take 0, then 3 and 4 would get compared, we would take 3, then 10 and 4 get compared, we take 4, this list is now empty, and so we take 10. We can then do the same thing on this other side, and now we say, take the 0 and 5 and merge it with the 8. Just like that. And so in this case, we now get 0 and 8 get compared, so we take the 0, 5 and 8 get compared, we take the 5. This list is now empty, so we just take whatever was left, and we get the 8. We can then merge those two, and so we get 0 and 0, we get 3, we get 4, we get 5, we get 8, and we get 10. And so we can see our list was sorted there. So in the event that it's not a nice power of 2, you just continue to do your merges as normal, and you bring in that extra number when it makes sense to do so. In this case, what we would see is that our merges, rather than forming a perfect binary tree, would rather form some complete binary tree. And we know that the height of this tree is also going to be logarithmic in some way, and so our complexity works out to be the same. Alright, so the merge sort is all about taking lists of length 1, merging them together, then taking those lists, merging them together, taking those lists, merging them together, and you keep going until you've merged all the lists together, and then you come out with a nice n log n. Okay, so we saw that a merge sort was some kind of recursive algorithm. Basically what we did was we partitioned the list into 2 separate things, and then we recursively called a merge sort on the left, and then recursively called it on the right hand side as well. A quicksort does a similar thing, where we use some method of partitioning the numbers into 2 different sets, and then we recursively call a quicksort on the left hand side, and recursively call it on the right hand side as well. So the first thing we need to do with a quicksort is to pick something called the pivot. And the idea is that we pick the pivot, and then all numbers that should go to the left move to the left-hand side of the list, and all the numbers that are bigger than the pivot should go to the right-hand side of the list. And so let's say that we randomly choose the number 5 as our pivot. Okay, we'll talk about what the different strategies are to select this later. But for now, you say we've picked the number 5 as our pivot. We then go through all the different numbers in the list and we decide whether they should go to the left or the right. So we first look at the number 3 and we see that 3 is less than 5, so it goes to the left. We then see the number 10. 10 is bigger than 5, and so it goes to the right. And as we go, we just fill up from the left or the right hand side until we've been through all the numbers. So we then get a 0, which is less than 5. We then get a 4, which is less than 5. We then get another 0, which is less than 5. So we carry on the left. Okay, we then see the pivot, so we ignore it for now. We get a 9, which is bigger than 5, so that should go to the right hand side. We then get an 8, which is bigger than 5, so it should go to the right hand side as well. And we've now gone through the entire list. The only number we haven't inserted is the 5, and we see that there's one open space left, so we can insert the 5 in that space. And because 5 was our pivot, we know that everything that's less than it is to its left hand side, and everything that's bigger than it is to its right hand side. So this actually means that 5 is now in the correct place in the sorted list. 5 will never have to move left or right, it's in its final position. So now that we've done that, we can then say recursively sort the left, recursively sort the right. So we can do the same thing. So on the left hand side, we pick a pivot. So let's say for now that the pivot is going to be 3. We then loop through all the numbers in that side of the list, and we say, do they go to the left or do they go to the right? So we see a 0, 0 is less than 3, so it goes to the left. We see a 4, 4 is bigger than 3, so it goes to the right. We see a 0, which is less than 3, so it goes to the left. We've then been through all the numbers, and there's one open space left, and so 3 gets put there. Just like that. And so, again, we know that all numbers that are bigger than 3 are on its right-hand side, and all numbers that are less than it are on the left-hand side. We also know that 3 is less than the previous pivot, which is less than everything on its right-hand side. So if there is a number that's bigger than 3, it will be on the right of this pivot, but it will still be on the left of this one. So we know that these two are finally in their correct space, and nothing will ever have to jump somewhere else. So we've now got a left-hand side and a right-hand side. So we look at the left, and we can say, okay, let's recursively do this again. So we pick a pivot. So let's say we pick 0, and then we loop through all the numbers in that list. And so we can say, okay, well, we see a 0. Okay, it doesn't matter if it's the same number. So we'll say that the 0 goes to the left. Okay, we've now been through all those numbers, and there's one open space. So we then insert the pivot, and we know that that is now in the correct place. We then recursively sort the left, and we see that actually that number, there's only one number in the list, and we said earlier that when there's one number, it's already sorted. So in this case, we can say that that one is also in the correct place, because it was just one number. So we've now gone left, we now need to go right. So again, we see that there's just one number, and so one number we can say it's already in the correct place. So we've now sorted the left-hand side of here, we now need to sort the right-hand side. So we pick a pivot. So let's say that in this case we choose the number 8 as our pivot. Right? We then loop through everything and we say, do they go left or right? So we see a 9, and so the 9 is bigger than 8, and so it goes to the right. We then see the next number, which is a 10. 10 is bigger than 8, so it also goes to the right. And then, so we've been through all those numbers. We see that there's one open space, and so that's for 8, which was our pivot. And now that we've placed our pivot, we can see it's in its final position. We then recursively sort the left, but we see that the left is an empty list. And so, because it's an empty list, then there's nothing to do. We recursively sort the right, and so we pick a pivot. So in this case, let's say we pick 10, and we say, loop through all the numbers and decide whether they go left or right. So we see the number 9. 9 is less than 10, and so it must go left. We've now been through everything in the list, and so there's one open space, and that's where we put the pivot. We recursively go left, and we see just a single number by itself, and so in that case it's already sorted, so it's in the correct place already. We go right, which is an empty list, and we can see that we've now sorted everything. Okay, so the idea of the quicksort is that you choose a pivot, you then partition the list, which means that everything smaller goes to the left of the pivot, and everything bigger goes to the right. And so once things have gone to the left and the right, we'll see that there's one more open space, and so we then put the pivot in that space. And now that the pivot's in that space, we know that it's in its final position. We then recurse left and right. We recurse left and then right. So let's do another example of this. Okay, so let's say we have some let's say we have a longer list this time. So let's say we've got Alright, so we have some longer list. Now, in this case, let's say to start off with, we need to pick a pivot, and so let's say that our pivot ends up being the number 8. Okay. We then loop through the list and we decide whether things go to the left or the right, so we partition it. So we say that 10 is bigger than 8, so it goes to the right. We see 5 is less, so it goes left. We see 13, which is bigger. We see 0, which is less. We see 4, which is less. We see 12, which is bigger. We see 15, which is bigger. We see -1, which is smaller. We see 42, which is bigger. And finally, we've got one space, and so that's where our pivot goes. And we know that 8 is in the correct place. We then do the left-hand side. So we pick a pivot. So let's say we pick the number 4. Well, let's say 5. Okay? So we've picked the number 5. So in this case, we then do our partition. So 0 goes to the left, 4 goes to the left, -1 goes to the left, and we've got one position left, and that's where 5 goes. That was our pivot, so it's now in the correct place. Let's do the same thing. So in this case, let's select the first item as our pivot. Right? So we've got 4. 4 is bigger than 0, so it goes to the right. We get -1, which is smaller, so it goes left. And then we've got one space where we can finally put the 0. So that's our pivot. It's in the correct place. If we go left, we see there's one item, so it's in the correct place. If we go right, there's one item, so it's in the correct place. We've gone left of 5. We now look right. Okay, it's an empty list, so it's fine. We've gone left of 8. We now go right of 8. So let's select the first item as our pivot. We can then say, okay, everything that's less goes to the left. So 15, less. 12, less than 42. 13, less than 42. 10, less than 42. So we've gone through all the numbers, and finally, in our last space that's open, we place the pivot. We then go left, so we select a pivot, and we partition the list. So 12 is less than 15, 13 is less, 10 is less. This means there's one more space, so 15 goes in, and that was our pivot, so it goes there. We then pick a pivot one more time. 13 is bigger, so it goes to the right. 10 is less, so it goes left, and we've got one more space, and so 12 goes into that space, and it was the pivot. We go left, there's one number, so it's in the correct place. We go right, there's one number, it's in the correct place. So we've gone left of 15, we go right of 15, there's nothing there. We've gone left of 42, we now go right, there's nothing there, which means that we've sorted the left of 8, we've sorted the right of 8, which means that our final list is now -1, 0, 4, 5, 8, 10, 12, 13, 15, and 42. So the way that we selected our pivot there was to simply take the first number in the list. And we see in some cases that worked out really well for us, and in other cases it didn't. So the first time we took the 8, and we see that it almost perfectly divided the list into 2. Okay, and that's what we want. The more balanced the two sides, the better. Whereas down here in these latter levels, we see that we selected 5, which was actually a bad selection because it basically just said take that number and move everything else over and then sort that. And we saw that if you only decrease the list by 1 every time, so we saw with the insertion and selection sorts that we went from n to n-1 to n-2, n-3, all of that. And we see that if we only decrease the list by 1 number every time, so if we continually select the biggest number or the smallest number, then we end up with this number of comparisons, right? Because then we're doing essentially a selection sort, because we've essentially selected the biggest number each time or the smallest number each time, and that means the list goes n, n-1, n-2, n-3, and because of that we end up with order n squared. Okay, I'll leave you to do the full calculation of that, but it's very similar to what we did with insertion and selection sort. So the idea of selecting a bad pivot at every step means that actually the quicksort does really badly. We end up with an n squared. If, however, we pick a really good pivot, which divides the list into 2 very well, then it means that this looks more like a merge sort, and we knew that with the merge sort we get n log n. Now, I'd like you to draw the graphs and see how they differ. So we'll see that the one looks like that and the other looks more like that. But go into Excel and just plot out some numbers like this, and you'll be able to see quite nicely that, in fact, the n log n is quite significantly better. Okay, so basically what we're saying is that for a pivot, we want to be sure that we're going to select a good pivot every time. If we select a bad pivot every time, we get quite bad complexity. But if we select a good pivot every time, then we get very good complexity. So what strategy can we use to try and make sure that we come up with the best pivot every time? So what we're going to do is we're going to say our first method of just selecting the first item in the list, okay, that doesn't seem to work out well. It means that you could potentially get a list that forces you to do the worst case every time. So we're rather going to say, can we select 3 random numbers? Select 3 numbers, and then if we take the median of those 3 and use that number as the pivot, we can see whether we do any better. So let's give this method a shot. So if we have our original list, so 8, 10, 5, 13, 0, 4, 12, 15, -1, and 42. So say now that we need to select a pivot. We randomly pick 3 numbers. So let's say we randomly, and by picking the numbers, what I mean is that we say we have each of these numbers has an index from 0, 1, 2, 3, 4, 5, 8, 9, like that. We then say, get the computer to generate a random number between 0 and 9. And so let's say the first random number we get is going to be 8. So we see that if we just picked that as our pivot, this would actually be really bad because that's the minimum number, and so that would cause us to get a bad selection, right? But then we pick another 2 random numbers. So let's say the next random number we get is 3, and the next random number we get is maybe 5. All right. Now, in this case, we then say, what numbers do those indices correspond to? So we got 3, and that's the index of 13. We got 5, which is the index of 4, and we get 8, which is the index of -1. So we take those three numbers and we pick the median, which is basically saying what sits in the middle of them when they're sorted. So we get -1, 4, and 13, and so the median there would be 4. So we're going to say use 4 as our pivot. All right. So now we can do our partitioning. So we can say, well, 8 is bigger than 4, 10 is bigger than 4, 5 is bigger than 4, 13 is bigger than 4, 0 is less than 4, 12 is bigger, 15 is bigger, -1 is less, 42 is bigger. Okay, we have one open space, and that's 4, our pivot. Okay, so we see that in this case it wasn't necessarily as good as when we chose 8, but we see that if we had just picked our random number, we might have ended up with -1, which would have been significantly worse than what we got here. So in this case, we can now do the same thing. Okay, there are only 2 numbers here, so selecting a pivot isn't super important. So let's just say we picked 0 as our pivot. All right, -1 is less, so it goes to the left. We put in our pivot. That's in the correct space. There's one item there, so it's in the correct space as well. If we look at the other side, we see we've got all these numbers, so we randomly select 3 numbers, like that. And then from there, now that we've randomly got those numbers, we say, which one is the median of them? Well, if they were sorted, it would be 5, 13, 15. And so the median is 3 in this case. 13 in this case. So we pick 13 as our pivot. And then we partition the list. So we say 42 is bigger. 15 is bigger. 5 is less, 10 is less, 8 is less, and then there's one space left, and so we put the pivot in. And we see in this case, this was actually the perfect pivot, right? Because everything, because the left-hand side and the right-hand side are almost exactly the same length. Have I skipped a number? 42, 15, 12. 12, sorry, I skipped 12. So that's 5, 10, and 8. Apologies, 5, 10, 8, and 12 would have gone there. Okay, so we see that it's not as good as I thought, but it's still not bad. It's still partitioned the list relatively evenly. So we've got 13 in the correct place. We can randomly pick 3 numbers. So let's say we pick 5, 10, 12. Okay, what's the median of them? That's going to be 10. So we say that 10 is our pivot. So 5 goes to the left, 8 goes to the left, 12 goes to the right, and we insert our pivot. On the left hand side, we've got 2 numbers, so we're not too stressed. We can just select a pivot, and we say 8 goes to the right, 5 then gets inserted, and it's in the correct place now. We've got a list of 1 number, that's sorted. We've got a list of 1 number, that's sorted. On the right hand side, we can select a pivot again, in this case as well. It doesn't really matter. So we've got 15, and we can say 42 is bigger, so it goes to the right, and then we insert the pivot, and there's 1 item left, so that's basically sorted. So we can see that in this case everything got sorted, all right, and so we can always be guaranteed that we will never hit the absolute worst case, because if we select the smallest or biggest numbers, then we still know that we're not going to have those as our pivot, because those can't possibly be the median of those numbers. Okay, so this strategy guarantees us that we're never going to get the absolute worst case. We can still possibly get some bad cases, but it means that we know that we'll never get the minimum or maximum as our pivot, and so we're guaranteed that our list length will decrease by more than 1 on each step. Okay, so this strategy is called the median of 3. And by selecting these 3 numbers randomly, okay, it means that there's no best or worst case in terms of whether the list is already sorted or unsorted or something like that. It means that it's incredibly difficult for it to actually happen where we get the worst case again and again and again and again and again, because we're not following some specific method. Later on, you'll learn how to do complexity analysis on algorithms that have a random component like this, and we come up with some kind of expectation where we can say with a certain degree of probability we know that this will be some specific type of complexity class. Now, in the same way that we had the merge sort, in the best case, when we continually divide the list in two, we're going to end up with an n log n complexity. And we said that in the absolute worst case, where we simply remove one item every time, we're going to end up with n squared. But by using good pivot selection strategies, like the median of 3, for example, we can guarantee that this order n squared won't happen, and that we simply end up with n log n every time. Okay. Cool. So that gets us through all of the different types of sorts. Those are the different ones you need to know for the exam. In the exam, I'm not going to be asking you about the complexity of the different sorts, but I do expect you to be able to actually perform the sorts. So if I give you a list of numbers, I expect that you're able to sort them using whatever strategy I ask you to use. Okay. Thanks for watching. If you have any questions, feel free to ask on the forum or to send me an email.